Good morning, students. Mr. Carver here. Here are two warm-up problems for you. Actually, three warm-up problems. Calculators, absolutely okay. Pause it, work them, and we'll check them. All right, so for number one there, you'll notice the sign of 2n plus 1 pi over 2 actually causes it to alternate. It's similar to negative 1 to the nth power. When I plug in 1, that's the sign of 3 pi over 2, which is negative 1. When I plug in 2, the sign of 5 pi over 2, which is positive 1, just oscillates back and forth between plus and minus 1. So essentially what I have is an alternating series. And the question for number one is looking for r sub n of x. And I'm looking for the number of terms. So let me just switch over here. All right, because that's an alternating series, I go straight to my calculator because you're looking for the term of the sequence that is less than or equal to 0.1/10,000th, 0.0001. So what I'm doing is I plug this into y sub 1, and I create a table. And remember, the lower index starts here at 1, which is where you want to start your table. So you'll notice that I'm starting my table right there at 1. And what I'm looking for is the first term that is less than or equal to 0.1/10,000th, essentially. And that is, it looks like the fifth term there. So this, remember, is the first neglected term. Once I get to the desired level of accuracy, that is this right here, I want to exclude it. And since I'm starting at 1, I'm going to use the first 4 terms. This would be then r sub 4 of x, 0.000025. All right, so then for the second part, get rid of some of this stuff. It's asking how accurate would my estimate be if I only use the first two terms. So I use the first two terms, and I cut it off right there at my second term. This then is my level of accuracy. So my r sub 2 of x will be less than or equal to 0.0. I can't read it. There we go. 0.0014. So this is the high side difference between the two-term estimation and the actual value of that infinite series, which is right here. All right, so let's go on then to the next question. All right, and I'm looking for the interval of convergence for this power series. And again, power series because it's got x's and n's in it, so I'm going to use the ratio test. I take the limit then as n goes to infinity. This is absolute valued, so I can disregard this part right there. It is a sub n plus 1, which is n plus 1 factorial, x minus 4 to the n plus 1, 3 to the n plus 1. Need to move this over just a little bit. Get rid of that. There we go. And then I flop with the original, so this is 3 to the n. This is n factorial. This is x minus 4 to the n. And then I just start canceling. So what I've got is one more 3 on the bottom than I have on the top. I've got an n plus 1 on the top. And I've got one more x minus 4 on the top. That's not x minus 4. That's x minus 4. I know that this is less than 1 because it is convergent. We're just trying to find where it converges to. So I take the limit then as n goes huge. Absolute value, n plus 1, x minus 4 all over 3, less than 1. This inequality will only be true because n continues to grow infinitely large if x is equal to 4. So it only converges at 4. And for those of you who love interval notation, it goes from 4 to 4, including 4. Right on. All right, so this is section 8.9, representations of functions. That's not how you spell that. By power series. So what we're going to do is we're going to generate Taylor and Maclaurin series, and we're going to build that into summation notation and write it as a power series, as opposed to writing it as a first few finite terms. So here's what I'd like you to do. Just a little review, a little more warm-up. What I'd like you to do is find, let's do a second degree polynomial estimation of f of x is equal to 1 over 1 minus x. And I want this to be a Maclaurin, so we're going to center this at 0. So pause it, do the work, and then hit play again because I'm going to put up the solution. All right. So if we're looking for a Maclaurin polynomial estimation, remember the first thing you do is find f prime, and f double prime, and then you evaluate each one of them where at the point at which it's centered. In this case, it's 0. So I plug 0 into each one of these, and I get these constants right here, and then I use the formula to build it. It is 1 over 0 factorial, x minus 0 to the 0, plus 1 over 1 factorial, x minus 0 to the first, and plus 2 over 2 factorial, x minus 0 to the second. So this will simplify to my second degree polynomial estimation, p sub 2 of x, which will be 1 plus x squared. And then if I want to take it all the way out, I've got p sub n of x would be equal to 1 plus x squared all the way out to x to the n. So if I asked you for a second degree polynomial estimation of 1 over 1 minus x centered at 0, it would be this polynomial right here. But this is really the part that I want to focus in on today. And I'm going to move this to the next page. So what I have is I've got my nth degree polynomial estimation can be written in with this pattern right here. And I think that you can see fairly easily that when I generalize this to summation notation, I can write this as a power series. That would be the sum from 0 to infinity of x to the n. Now here is the fascinating part. And yes, it's almost Friday. Or for some of you, actually, it is Friday. This is equal to, then, my original function, which is 1 over 1 minus x. So that is. Now, in most cases, as long as we assume that n is infinitely large, we can say that this actually is equal. If n is finite, we would say that that's roughly equal. But you get the idea, that this power series is a representation of this functional value right there. Okay, now what I want you to do is go back in time. Think to yourself, way back in time, back to Honors Algebra 2, and potentially in Honors Pre-Calculus. Do you remember this formula? Actually, it's also from this class as well, just about 6 or 7 weeks ago. It looks like this. S sub infinity is equal to a sub 1 over 1 minus r. Isn't this the formula for the infinite sum of a geometric series with a ratio of r and a first term of a sub 1? So a sub 1 over 1 minus r. And what you'll notice here is that this function is actually in that form. So this is my a sub 1, this is my r. And this section today is showing you how to tie in functions that are written in this form and then generalizing it into the formula for the geometric series, which is the sum from n equals 0 to infinity of a sub 1 times r to the n. That is going to be equal to a sub 1 over 1 minus r. This power series is the summation notation representation of a function written in that form. Fascinating. Now this is great news because it's a shortcut. I actually don't have to go through all of this anymore as long as I have a function that's written in a friendly form. This is certainly written in a friendly form, so I can just cut to the chase. I've got the sum from n equals 0 to infinity. I write down my a sub 1, I put in my r, and I raise it to the x power. This, then, is actually what we were trying to get in the first place. So today is all about taking advantage of this shortcut and applying it to formulas written in a certain form. Now I know this is a little convoluted. They're just giving you things that are close to the form that you need, but that's okay. They're trying to tie in together the fact that the infinite summation can be written in power series form fairly easily. That's really what 8.9 is all about, and that's where we're heading today. All right, let's work a few examples. All right, we'll start off with an easy example. By the way, the homework tonight will say, find a power series for something like f of x is equal to, let's do 3 over x plus 2. And then they're going to tell you where it's centered at. Let's keep it easy. For this first one, we're going to center it at 0, so it's a Maclaurin polynomial. Now, what we could do is, again, we could go through all the same steps as before, derive this once, twice, 3 times, 4 times, etc., until we get enough of a pattern to develop the power series. But this is really, really close to a friendly form, so I just need to manipulate it, and then I can use the pattern that we just talked about to put it into power series form. Okay, so just as a reminder, S sub infinity is equal to a sub 1 over 1 minus r. So this is what we're going for, which means, first of all, that this has to be a 1. So I'm going to take my original function, my f of x, and I'm going to manipulate it. This is 3 over x plus 2. First, I'm just going to switch the denominator around. That's 3 over 2 plus x. And then what I want to do is I want to make this a 1. So I'm going to divide everything through by 2, which is going to give me, this is going to be 3 halves over 1 plus 1 half times x. This is f of x, and now I've got it in a friendly form. So I'm going to take this now, and I'm going to build it into a power series. This power series always starts at 0. In fact, all power series start at 0. And as you develop them, you will always start them at 0, and you go to infinity. And I'm going to have a sub 1, 3 halves. And then, let's see. All right, just wanted to scoot that over just a little bit. So I've got a sub 1 and my r. Now you got to be careful here. This denominator is written as 1 minus r. So in this case, this is going to be 1 minus negative 1 half x. So my r is negative. So this is negative 1 half x, and that's all to the n. All right, so I would like you to clean this up a little bit. First, I'm just going to take this constant and move it out to the front. Why? Because I can. This is 3 halves. This is the infinite sum from n equals 0 to infinity. And then what I'm going to do is I'm going to take this portion right here, and I'm going to split off the part that makes it alternate, which will be negative 1. I don't like orange. This is negative 1 to the n times 1 half x to the n. I would like it like this, and here's why. Because eventually I'm going to be asking you about intervals of convergence for this. So it's nice to get things like the constant out of the way. It's also nice to split off the part that makes it alternate so that when you use the ratio test, you're just using this part right here, and it makes it super, super easy. It's also easy for me to grade if everyone's doing it in the same manner. So thank you very much. This then is your answer. This is the power series representation for 3 over x plus 2 centered at 0. And you can tell right from this portion right here that that is centered at 0. C is 0. All right, let's do a couple more. Okay, so now we're going to do f of x is equal to 3 over 2x minus 1, and I'm going to move it around a little bit. Now we're going to do a Taylor, so I'm going to center this thing at 2. So I really need to manipulate this. So I think let's start off by centering this thing at 2 first. So now if I rearrange this denominator and I were to put it into a sub 1 over 1 minus r form, this portion right here is going to be centered at 0. I don't want it centered at 0. I want it to be centered at 2. So here's what I'm going to do. I'm going to do some algebra to this. This is going to be 3 on top. And what I want to do is I want to make my x so that it's centered at 2. I'm going to force that to be x minus 2. I'm just going to change it. Now listen, you can't just change things arbitrarily. If I actually take away a 4, and by the way, this is just like completing the square, I'm taking away 2 negative 2's. I want to add that back. And then, of course, I've got the minus 1 from my original problem up here. Now, just to make sure that you've done this correctly, If you simplify that bottom, you should get back to the original problem. You have to get back to the original problem, otherwise you've changed things and you've screwed it up. So let's just check this. This is going to be 3 over 2x minus 4 plus 4 minus 1, which gives me 3 over 2x minus 1. I'm good to go. Check. So I know I've done it right. All right, so let's get rid of all this. Okay, and then I'm just going to clean up what I have. I'm going to continue working with this form right there. So this is going to be 3. This looks like 3 plus 2 times x minus 2. And all I'm doing is just using algebra to move stuff around and get it into a friendly form. Again, that friendly form is a sub 1 over 1 minus r. Okay, so I'm almost there. Now again, if you recall, this has to be a 1. So just like in the previous problem, what I'm going to do is I'm going to divide everything by 3. So I get 1 on top. This gives me 1 plus 2/3 times x minus 2, which is now a very, very friendly form. I can take this and build my power series. I've got a power series starting, infinite sum rather, going from 0 to infinity. I've got my a sub 1, which is 1, and I've got my r, which is negative 2/3 times x minus 2, all to the n. And then, of course, I would like you to clean this up. So I'm going to separate the negative part from the negative alternating part from the rest of my a sub n. So this will be the sum from n equals 0 to infinity. Don't need to write the 1. I've got negative 1 to the n. And I've got 2/3 x minus 2, all that to the n. Now, this is my power series representation. Incidentally, what you'll notice here is that this checks. This r here is centered at positive 2. So I have a power series centered at positive 2. Now, if I were to ask you for the interval of convergence, I have a little secret for you. An interval of convergence, what you're doing is, this is S sub infinity for a convergent geometric series. So remember that a geometric series, not a sequence, but a series will converge if the absolute value of r is less than 1. So if I ask you for the interval of convergence on this, and I do the ratio test, I'm going to have one more of these on the top than I am on the bottom because I disregard this. So I've got 2/3 x minus 2, absolute value is less than 1. Now, if I go ahead and solve this, I'm going to get an overall interval of convergence. But remember, from previous sections, I need to check the endpoints. The secret is this, that the endpoints will never, ever work when you are building a power series from this form. And the reason is because of this inequality here. This inequality gives you the endpoints. It can't work because it's less than 1. Now, that's not the case for power series that are not geometric. Remember, you are building geometric series here, which is why in 8.9, the endpoints never work. Now, you'll need to solve this to find the endpoints. So let's do that really quickly. I've got the absolute value of 2/3 x minus 2 less than 1, which gives me 2/3 x minus 2 less than 1, 2/3 x minus 2 greater than negative 1. Multiply both sides by 3/2, x minus 2 less than 3/2, x minus 2 greater than negative 3/2. And I'm going to add 2 to both sides, so x is less than, what is that, 7/2. And then I'm going to add 4/2 to this, so x is greater than or equal to, greater than 1/2, which means my interval of convergence for the power series that I just found goes from 1/2 to 7/2. And again, the secret is the endpoints never converge, so you exclude them. If you'd like to show some work, you could say that the endpoints are excluded because of the geometric series test. All right, guys, thanks for hanging in there. I just got one more to work for you. If you've got something like this, that function right there, it's certainly not in a friendly form. It's in a horrible form, nowhere close to a sub 1 over 1 minus r. I'm going to center this thing at equal to 0. One thing I do notice is that I have a factorable denominator. That's right, class, that's right, it's going to be partial fractions. So recall, this is going to be equal to 4x minus 7. This is all over, that factors to 2x minus 1 times x plus 2. So I'm going to do partial fractions a over 2x minus 1 plus b over x plus 2. If you'd like to pause it and work on that, be my guest. All right, that's what you should have gotten. A is -2, b is equal to 3. I'm not going to work through that because we've been doing that now for a couple of chapters. So now I take my a, I put it on top of the a fraction, or where it belongs, and b as well. So then what I want to do is I want to have a separate power series for this function and for this function, and then I'll work on them separately to determine an overall interval of convergence. All right, so let's do that. So this first one here, I've got -2, -1 plus 2x. This is going to be 3 over 2 plus x. So on this one, I'm going to divide by -1. This one, I'm going to divide by 2. So that's going to give me 2 over 1 minus 2x. And this is going to give me 3/2 all over 1 plus 1/2 x. All right, these are definitely friendly forms. So my first power series goes from 0 to infinity. This is going to be 2 times 2x to the n. This one's going to be 3/2. And again, I'm moving my a sub 1 out to the front. Does not impact intervals of convergence. So this is 2 times the sum from n equals 0 to infinity, 2x to the n, plus 3/2, sum from n equals 0 to infinity, of -1 to the n, 1/2 x to the n. All right, so if I'm just looking for the power series representation of that sum, you can stop right there. If I'm looking for the interval of convergence, you're going to have to do a couple more steps. So let me just make some room. I'll go to the next page, and we'll work on those. All right, so I've copied them over onto the second page. I'm going to do intervals of convergence for each one of these individually. Again, for both of these, I'm going to take the limit as n goes to infinity. I think you guys can see I've got one more on the top here than I do on the bottom, so that's just 2x is less than 1. I'm kind of skipping that step of the ratio test. Hope that's okay. The same thing here. And by the way, these are just going to turn into geometric sequences or geometric series. So I hope this makes sense, that this is really just my r, and my r has to be less than 1 in order to converge. So this is x over 2 is less than 1. So if I solve this, I get 2x less than 1, 2x greater than -1, x over 2 less than 1, x over 2 greater than -1. This is x is less than 2, x is greater than -2. So this goes from -2 to 2, not including the endpoints because of the secret that I told you. These are, again, geometric series. The second one here, then, is I actually just noticed a mistake here. This is x is less than 2. X is greater than -2. This actually should be 1/2. Good morning, Mr. Carver. So it's -1/2 to 1/2, not including the endpoints, and this goes from -2 to 2, not including the endpoints. Now, if I'm looking for the interval of convergence for the sum of these two power series, it will be the overlap of the two intervals, which means it will be the more narrow of the two, which means my interval of convergence for the sum will go from -1/2 to 1/2. Incidentally, both of these are centered at 0, which is the way I constructed them. But again, it's the more narrow of the two intervals of convergence. All right, guys, that's all I've got for today. I hope this was clear. Email me if not, or I'll see you on the video conference next week, and hopefully we can get everything cleared up. And just hang in there. We're almost done with Chapter 8. Thanks.